Today, we're tackling, well, maybe the biggest puzzle out there, the quantum enigma. It's this deep, almost philosophical mystery right at the core of modern physics.
Yeah, it really is. Sometimes you hear it called the skeleton in the closet of physics.
Skeleton in the closet, why's that?
Well, because quantum mechanics, QM, is just incredibly successful. I mean, staggeringly so. Not one prediction it's ever made has turned out to be wrong. Not one.
Okay, that sounds pretty good. What's the problem?
The problem is that it completely blows up our everyday intuitive understanding of, well, reality itself, how the universe actually works.
Right. And the sources we looked at really point to Einstein as being maybe the most famous person deeply bothered by this.
Oh, absolutely. He famously hated the idea of spooky action at a distance.
And he had that famous question, didn't he, about the moon?
He did. Does the moon exist only when we're looking at it? If observation creates reality, that's the sort of uncomfortable place QM takes you.
Okay, so that tension, that's what we're diving into today.
Exactly. The mission for this deep dive is really to unpack these core quantum ideas and show you, the listener, the huge questions they raise about reality, about measurement, and maybe even about consciousness.
It sounds like a wild ride. Let's get into it.
So to really appreciate how much of a bombshell quantum mechanics was, you kind of have to see what came before it. The classical worldview.
The Newtonian world.
Precisely. Built on foundations from people like Galileo, who really pushed the experimental method, and of course Newton with his laws of motion. Universal deterministic laws.
Yeah, that universe felt, I don't know, solid, predictable, like a giant clockwork machine. You know all the pieces now, you know the whole future. Physics felt done.
It did.
Yeah.
Everything seemed to be operating on a predetermined path. But then physicists started looking really closely, down to the atomic level.
And the clockwork started to break down.
Violently break down, you could say. It wasn't like they wanted a new physics. It was forced on them by experiments, things classical physics just couldn't explain.
Like the ultraviolet catastrophe, that sounds dramatic.
It was, theoretically speaking, a huge crisis.
Hmm.
Classical physics predicted that any hot object, like a glowing piece of metal, should radiate infinite energy at high frequencies in the ultraviolet range.
Which obviously doesn't happen. You'd be vaporized just standing near a fireplace.
Exactly. So something was deeply wrong with the classical picture, and this is where Max Planck comes in. He made what he himself called an act of desperation.
What did he do?
To make the math match reality, he had to make a radical assumption that energy didn't flow continuously, but came in tiny, discrete packets. He called them quanta.
And introduced that famous constant, Planck's constant H.
That's the one. But it was Einstein who really ran with the idea. He used these quanta, calling them photons, to explain something else entirely, the photoelectric effect.
Where light hitting metal kicks out electrons?
Right. He showed that light itself, which everyone thought was just a wave, was acting like a stream of particles, these photons.
Such a revolutionary idea, wasn't it? Even his Nobel Prize citation kind of tiptoed around mentioning photons directly.
They did. It was too strange for many at the time. And then Louis de Broglie took it a step further.
He flipped it.
He did. He said, well, if waves like light can be particles, maybe particles like electrons can also act like waves. Wave-particle duality for everything.
Which set the stage for Schrödinger.
Erwin Schrödinger. Now, ironically, he personally disliked the whole idea of these random quantum jumps.
But he gave us the equation.
He gave us the foundational equation, yes. Schrödinger's wave equation. It essentially replaced Newton's laws for the quantum realm. It's the new universal law of motion down there.
But there's a catch. A huge one.
A massive catch. Unlike Newton's need equations that tell you exactly where something is and where it's going, Schrödinger's equation only gives you probabilities.
Probabilities of where you might find the particle if you look.
Exactly. It describes a wave of potentiality possibilities. The randomness seems to be fundamental, built right into the fabric of reality at that level.
And it only becomes definite.
When you make an observation, when the potential somehow turns into the actual.
Okay, this leads us straight into the experiment that Richard Feynman famously said holds all the quantum weirdness. The two-slit experiment.
Yes. It's kind of the perfect illustration of the core paradox. It's deceptively simple.
So you fire single particles, like electrons or atoms, one by one, towards a barrier with two narrow slits in it.
Right. And behind the barrier, there's a detector screen to see where they land. Now, if these were just tiny billiard balls, you expect two distinct lines on the screen right behind the slits.
Makes sense. Particles go through one slit or the other.
But that's not what happens. Instead, you get this pattern of multiple bands, light and dark stripes. It's called an interference pattern.
Which is the classic signature of a wave.
Exactly. It's the pattern you get when a wave passes through both slits at the same time, and the two resulting wave fronts interfere with each other, canceling out in some places and reinforcing in others.
Wait, but you said we're firing single particles. How can one electron go through both slits simultaneously and interfere with itself?
That's the mystery. It behaves like a wave spread out in space. But here's where it gets even stranger.
Go on.
If you place a detector right at the slits, specifically to find out which slit each particle goes through,
Okay, now we're watching closely.
as soon as you do that, the interference pattern vanishes completely.
It's gone. What do you see instead?
You see exactly what you expected originally. Two distinct lines right behind the slits. The electron suddenly acts like a localized particle again, choosing just one path.
So, just by checking which path it took.
You destroy the wave behavior. The act of measurement, of observation, seems to force the particle out of its wave-like state. It's as if our choice of what to measure determined the particle's past behavior.
That's deeply weird. How do physicists even deal with that?
Well, the standard approach, developed mostly by Niels Bohr and Werner Heisenberg, is called the Copenhagen interpretation. It's pragmatic, but philosophically challenging.
What's the core idea?
The core idea is pretty mind-bending. Observation doesn't just disturb what you're measuring. It fundamentally produces the result. Properties like position or momentum don't really exist in a definite way for a quantum particle until you measure them.
So before you measure, it's just potential.
A cloud of potentialities, yes. A superposition of possibilities described by the wave function. And observation is defined quite broadly, basically any interaction with a large macroscopic system, like a detector.
Okay, so key ideas are probability and this thing called complementarity.
Right. Complementarity is Bohr's concept. It says that certain properties, like being a wave and being a particle, are complementary aspects of reality. You can design an experiment to see one aspect or the other, but you can never see both at the exact same time. They're mutually exclusive views.
Choose your measurement, choose your reality, almost.
In a nutshell, yes. And this strangeness, particularly complying superposition to big things, is what led Schrödinger to come up with his famous thought experiment.
Ah, the cat. Schrödinger's cat, everyone's heard of it, but what was his point?
His point was to show how absurd, he thought. It was to take quantum superposition literally and apply it to everyday objects.
So remind us of the setup. It's a bit grim.
It is. You imagine a cat sealed in a box. Inside, there's a radioactive atom, a detector, a hammer, and a vial of poison gas. If the atom decays, a quantum event, it triggers the detector, which releases the hammer, which smashes the vial, killing the cat.
Okay.
Now, according to standard quantum math, until someone opens the box and observes the system, the radioactive atom is in a superposition of both decayed and not decayed.
Which means?
Which means, if you follow the chain of entanglement, the detector is both triggered and not triggered, the hammer is both fallen and not fallen, the vial is both broken and intact, and therefore, the cat is simultaneously alive and dead.
A superposition of life and death, that's what he found absurd.
Exactly. He cooked up this scenario to argue that quantum mechanics must be incomplete or just plain wrong when scaled up. If tiny atoms aren't real until observed, how can a big collection of atoms like a cat be real? Or be stuck in this impossible state?
So, are physicists saying my cat might be half dead right now until I look?
Well, that's the logical extension if you apply the formalism directly. Of course, most physicists today would argue that something like a cat can't really be isolated like that. It's constantly interacting with its environment, the air molecules, the box walls, thermal radiation.
So, the environment is constantly observing it.
That's the idea behind decoherence. These constant interactions essentially measure the cat continuously, forcing it into a definite state, alive or dead, almost instantly, long before a person opens the box.
But it still doesn't fully solve when or how that final collapse into one reality happens, does it?
No. That point of collapse, the transition from quantum potential to classical actuality, remains a deep puzzle. And this whole mess, the ambiguity, the role of observation, this is what Einstein really pushed back against. He wanted a real world out there, existing whether we look or not.
That led to the EPR paper, right? Einstein, Podolsky, and Rosen in 1935.
That's right. They constructed a brilliant argument designed to show that quantum mechanics must be incomplete. It involved those spooky correlations.
Spooky action at a distance again. How did the argument go?
They imagined two particles that interact and then fly off in opposite directions. Let's say they're entangled, meaning their fates are linked. QM says if you measure a property of particle A, say its spin, You instantly know the spin of particle B, no matter how far away it is, could be light years.
Instantly. That sounds like faster than light communication.
Well, that was Einstein's point.
Mhm.
He argued either A, that particles had these properties predetermined all along, like hidden instructions QM didn't count for, making QM incomplete, or B, measuring A somehow instantaneously influenced B across space, which violated relativity's speed limit. Spooky action.
And for years, that was just a philosophical debate. Bohr versus Einstein.
For decades, yes. It seemed like metaphysics, not physics, until John Bell came along in the 1960s.
The unsung hero, you called him. What did Bell do?
Bell did something incredible. He took this philosophical argument and turned it into a concrete, testable prediction. He devised a mathematical theorem, Bell's theorem.
Often called the most profound discovery in science in the latter 20th century. High praise.
It deserves it.
Mm.
Bell showed that if you assume both locality, no spooky action, influences can't travel faster than light, and realism, properties exist objectively before measurement, like Einstein wanted.
Okay, the common sense assumptions.
Right. If both of those hold, then the statistical correlations between measurements on entangled particles like A and B cannot exceed a certain mathematical limit. These are known as Bell's inequalities.
So he gave us a number, a limit based on classical intuition.
Exactly. Perform the experiments, measure the correlations. If they stay below Bell's limit, Einstein might be right. If they exceed it,
Then our classical intuition about reality and locality, or both, must be wrong.
precisely. And the experiments have been done many times with increasing precision.
And the results.
The results consistently, overwhelmingly, violate Bell's inequalities. The correlations are stronger than any local, realistic theory could possibly allow.
Wow. So the universe itself told us. What?
It told us that our comfortable classical picture is fundamentally wrong. We cannot have both objective reality properties existing before measurement and locality, no faster than light influence. At least one has to go.
So we have to choose. Either things aren't real until measured, or there is some kind of spooky, instantaneous connection across space.
That's the stark choice experimental results force on us. Entanglement isn't just a theoretical quirk. It seems to point towards a profound, universal connectedness. Everything that has ever interacted might remain linked in some way.
This is experimental metaphysics, truly. But it's not just philosophy, is it? You mentioned technology.
Well, absolutely not just philosophy. It's estimated that something like 1/3 of the entire global economy depends on technologies born from understanding quantum mechanics.
Like what?
Lasers, transistors, which are the basis of all computers and smartphones, MRI machines in hospitals, even things like modern LEDs and quantum dots in TVs, all rely on harnessing these weird quantum principles. So the theory works spectacularly well for building things, yet when we try to understand its foundations, particularly that moment of measurement, the wave function collapse, we hit a wall. Or maybe something non-physical.
Which brings us inevitably to the most controversial part. The role of the observer. Specifically, does consciousness play a part?
It's the elephant in the quantum room. You have figures like Nobel laureate Eugene Wigner, who stated quite bluntly back in the day that you couldn't fully formulate QM consistently without referring to consciousness.
Why did he think that?
Well, it goes back to the measurement problem. John von Neumann, a brilliant mathematician, analyzed the process step by step. The quantum system, like an atom, is in superposition. It interacts with a detector. Now, the detector is entangled and also in superposition. That interacts with a computer.
The superposition just keeps spreading.
Exactly.
Mm-hmm.
Von Neumann tracked this chain of entanglement outwards. Where does it stop? Where does potentiality become actuality? He argued the chain only breaks, the wave function only collapses when it encounters something that cannot itself be put into superposition,
And that something is.
the conscious mind of the observer.
So, in his view, consciousness itself causes the collapse. The buck stops there.
That was his controversial conclusion. The collapse happens at the interface between the physical measuring device and the subjective awareness perceiving the result. The quantum enigma meets the mystery of consciousness head-on.
And there's another angle too, right? About free will.
Yes. Think about the experiments, like the two-slit. The experimenter makes a choice. Do I measure which slit particle behavior, or do I let it go unobserved, wave behavior?
Our choice seems to influence the outcome.
If we assume the experimenter has genuine free will, then their conscious choice seems to directly impact the physical reality that manifests. It forces the wave function to collapse into one state or another based on the question asked.
But if free will is an illusion, if the experimenter's choice was predetermined,
Then the outcome was also predetermined. And maybe the apparent randomness is just our ignorance. But QM feels fundamentally random. This ties into what David Chalmers calls the hard problem of consciousness. How does subjective experience arise from physical stuff? How does our inner world connect to the outer quantum world?
Are there theories trying to formally link them?
There are a few, yes. They're speculative, of course. You have Roger Penrose and Stuart Hamroff suggesting consciousness actually arises from quantum computations happening inside microtubules in brain neurons, causing an objective collapse.
So consciousness is a quantum effect itself.
In their view, yes. Then you have theories like Henry Stapp's, which lean more towards Wigner and von Neumann, arguing consciousness plays a more active causal role in selecting outcomes, collapsing the wave function through intention.
So mind directly influencing matter at the quantum level.
That's the implication. Whichever interpretation you lean towards, even the more mainstream ones that try to avoid consciousness, the core issue doesn't vanish. Quantum mechanics seems to tell us that its encounter with the observer, with measurement, isn't just some minor detail. It's central.
It applies in principle to everything. The observer isn't separate.
Right. It suggests a clean split between the subjective in here and the objective out there, which classical physics took for granted. Just doesn't hold up. We seem to be participants in constructing reality, not just passive onlookers.
Which really brings us full circle. This deep dive shows just how profoundly quantum mechanics challenges our basic assumptions. It suggests physics itself bumps up against consciousness.
It absolutely does.
Yeah.
We're left with these enormous open questions about the fundamental nature of existence, about what constitutes reality. The very success of the theory forces these questions upon us.
So for our final thought, something for you, the listener, to chew on. It comes from Stephen Hawking. He was pondering the ultimate theory of everything, the equations governing the universe.
And he asked this incredibly profound question. Even if there is only one possible unified theory, it is just a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe?
What breathes fire into the equations?
And maybe, just maybe, the insights from the quantum enigma suggest an answer. The fact that consciousness seems inextricably linked to the manifestation of reality. Well, it hints that perhaps life, mind, awareness aren't just accidental byproducts in a mechanical universe,
But something more fundamental.
perhaps something essential in breathing the fire, in making the universe actual. It suggests maybe we have a far larger role to play in shaping existence than we ever imagined. That's a thought that really turns the old scientific picture inside out.